button it some more.
Mr. Kendrick. Okay. He had a lecture on what cleavage actually meant. So, Mr. Kendrick. Yeah.
Okay. This is where we were, wasn't it? Synthesis?
Yes.
Is that where we ended? Excellent. So, this is where we take basic chemicals and create more complex chemicals, like we did with magnesium and oxygen. We took very simple simple elements, magnesium and oxygen, combined them, made a more complex one, magnesium oxide. Sometimes these are called combination reactions. So there's a lot of vocabulary that can be used interchangeably. This would be one of them. So this might be a good flashcard of synthesis, or synthesis synonym on one side, and then you could put combination reaction on the back. It typically requires energy to be put in the system for it to happen. It's endothermic. And we saw that with the magnesium and the oxygen. I had to put it in the flame to get enough energy for the reaction to start occurring. So it was endothermic. Took that energy in. Okay. So often we have, more reactants than products in a synthesis reaction or a combination reaction. The elements generally form compounds. And here's our example that we've talked about multiple times now. We have H2 plus O2 forming H2O. Is that balanced? No, not yet. So what do I have to do to get this one balanced? Yeah, 2 there, 2 there. Now I've got a balanced reaction. It's much happier when it's balanced. Okay. Wow, that went quickly. Okay. So decomposition is the opposite of a synthesis reaction. And you've heard the word decompose before. It's breaking into parts. It's like having a compost heap in your house, at your house, not in your house, hopefully, where it breaks into its part. It decomposes. The chemicals are breaking down into more simple ones. And typically it's going to release some energy, be slightly exothermic, or majorly exothermic, depending on what the reaction is. So we had a demo yesterday called Elephant Toothpaste. Kind of worked in this hour. Worked great 6th hour. 5th hour, it moved that much. It was so pathetic and sad. I felt bad for 5th hour. You guys at least saw a little bit of the excitement of Elephant Toothpaste. That was a decomposition reaction. What was that? Yes, you can look it up on Jen the Kim Lady for lots of fun ones. So with this one, you had H2O2, and it decomposed into hydrogen and oxygen. And it was exothermic. If you could get close to the graduated cylinder in a spot where there was no chemicals, it felt hot to the touch. It was releasing energy, and we kind of saw the steam coming up off of it too, a little bit, much more in 6th hour, but a little bit in here. So exothermic, releasing that energy. Our general patterns for it, often we have more products than reactants. And here's an example that you're going to see in the lab tomorrow. So we're going to take some solid copper and react it with nitric acid, which nitric acid has to be kept in its own acid cabinet. Like you can't even keep it with the other acids because it's very reactive and doesn't play well with others. Yeah. Yep, this one will be done as a demo in the hood. And it forms copper 2 nitrate, nitrogen dioxide, which when you read through the lab you'll find out why we do it in the hood, because of that NO2, and water. So notice here that the nitric acid is breaking down into more simple compounds, both the copper 2 nitrate, and the nitrogen dioxide. Combustion. Combustion is always a fun one. It's where we get fire. And it's where we have a reaction of a chemical with oxygen gas. And it is very exothermic. So it's going to release a lot of energy. For the combustion of a hydrocarbon, the products are always going to be carbon dioxide and water vapor. So what it means by hydrocarbon is a bunch of carbons and hydrogens together. Sometimes oxygen is mixed in there as well. Oxygen gas must be one of the reactants. Must. I'm going to get my goggles on. You don't need yours, but you do need to be past the blue line here. But you can come closer if you want, so long as you're not past the blue line. Hydrocarbon has to be in the gas phase for the reaction to occur. So I'm just speeding up the particles some so they go from the liquid state into the gas state. And I need some oxygen in the head. I'm assuming some oxygen in here, but I want to add some more oxygen to it. So I'm just going to add some more oxygen and make sure there's plenty of oxygen for my hydrocarbon to react with. Okay, I'm keeping the gas in there right now because what would happen if there was nothing covering it? Yeah, it would just escape, fill up in their own. Need some serving machine snacks. Combusted. Feel this now. Finally, something warm in the classroom. It's amazing. Yeah. Yeah, it's excellent. I know. That was a lot of work for
The one family song site. And bottled milk.
So it was exothermic. So warm. Isn't it amazing? What do you see at the bottom of this Yeah, there's a liquid in here. There's a liquid at the bottom. Is that liquid at the bottom all the ethanol that I put in there? No. What should it be? It should be water, yeah. So my water that was in here condensed. I would definitely not want to drink it, especially since there's matches that are in there. Yeah.
Is that like
gross.
pure water then?
No, because the reaction probably didn't happen 100%.
If it were to happen, it'd be like,
It would be completely clear water and you could drink it, but I wouldn't trust it. So that was one little combustion for us. We also have combustion of gasoline in our engine every time we drive our cars, and that is with octane. C8H18 is called octane. I just want to stand over this bottle for the rest of the day until it gets cold and then do it again. Yeah, so last year when I did it for family science night, I didn't let it cool off enough in between, and so it was still kind of warm, and then I did it again, and it melted all the way, and it was bad. These bottles are hard to find now without the handle on the side. That was bad. Lesson learned. Leave a whole class period in between. Okay, so is this reaction balanced? No, it is not. So we are going to rewrite it and make sure that we can balance it correctly. So octane, C8H18. It comes out as a liquid when you're pumping it at the gas tank, but is it a liquid when it's reacting? No, it's got to be a gas. So we'll put a G behind here. And what does it have to react with? Oxygen. So just OG, right? O2, yeah, it's diatomic. Good. Thank you. Okay, and it's forming H2O, which could condense right away or it could be a gas. I would give you points either with liquid or gas there. Plus carbon dioxide, CO2. That one is definitely a gas. Okay, we'll set up our counting like we did yesterday. So here's my two sides. I've got carbon, hydrogen, and oxygen on both sides. Okay. Carbon on my reactant side. Shout out how many there are. 8. Excellent. Hydrogen, shout it out. 18. Oxygen, shout it out. 2. Okay. Product side. Shout it out for carbon. 1. Hydrogen. 2. Not enough shouting. Oxygen.
2.
3. Yes. I've got it in 2 parts. I've got it here and here. 2 plus 1 is 3. This is why we said we're going to leave hydrogens and oxygens for last when we balance. It's because of situations like this where it gets a little bit trickier. I've got it in multiple places. I don't like dealing with it when it's like that. So I'm going to save that oxygen for last. Let's do the carbons first. So what can I do to get this 1 to be 8? Multiply by 8. So I'm going to put a coefficient of 8 right there. My carbons are now 8. But I no longer have 3 oxygens. How many do I have? 17.
Oh,
Ooh, that's okay. So 8 times 2, that's the 16, plus the 1 more that's still there, 17. See how that oxygen is just not looking pretty? Yeah. Okay, hydrogens now. I have 18 on this side. Got them in one spot over here, so what should my coefficient be? 9, yeah, so that I get to 18. Exactly. So I need to get to 18, so I'm multiplying water by 9. So I have 9 moles of water as a result of this reaction between octane and oxygen. So everything's looking good so far. My carbon's good, my hydrogen's good, except for my oxygen. My oxygen changed here as well. So I had 17, I don't anymore. I have 16 from here, and 9 from here. 25, yeah. 25, that's okay. I've got 25 total. Now there's one instance where we can use a fraction. And this is that one instance. One instance in balancing where we can use a fraction. What we can do is say, well, I know if I have something divided by 2 and I'm multiplying it by 2, that whatever answer I get is whatever my numerator is. So I could do 25 halves multiplied by my O2, and I would get 25. From knowing that I needed 25 because of what's on my product side. So I need 25 because I have 25 over here. So if I have 25 halves multiplied by the 2 in my O2, then I just have 25. If you don't like that fraction, you have a question? Yeah.
So would you just leave it at 25 O2?
25 halves O2 would be the correct answer. Or there's one other possibility, Natalie. That's our other possibility. So if you're like, that looks really funky to me, you can go through and take everything multiplied by 2, both the reactants and the products.
So then you just leave 25.
Yeah, so you would have 2C8H18 as a gas, plus 25 O2s. That was a really weird looking O2, sorry. That's a gas, forming 18 waters in the liquid state, plus 16 CO2s in the gas state. So either one of these reactions would be perfect. It just depends if you like the way that this 25 halves looks or not. Don't ever do a decimal though. Bad form. We don't do that.
Should you make it a mixed fraction, or do you want it
Want it as an yeah. Other questions before we move along? So, we saw this, we needed oxygen, we got carbon dioxide and water. We're going to talk later on in the school year what happens if we have a combustion reaction that does not go to completion. We're going to get lots of side products. We're going to get some other, not octane, but other types of hydrocarbons as a result. We're not worrying about that here. We're going to say that everything works perfectly and it's a complete reaction at this point. We also have single replacement or displacement. Those words can be used interchangeably. So again, you might want a flashcard that has single replacement synonym, and on the other side says single displacement. It typically involves a solution in either a solid or a gas. So the gas would be pumped into the solution, the solid would be put into the solution. It's going to produce a visible product. So one product that is not soluble, not going to dissolve in the aqueous solution. And it's typically exothermic. Now some of you were looking up here when you came in, which is good. This is copper chloride solution. What color is it? Blue, green, yeah, kind of turquoisey. This is how the solution is to start with. I took some aluminum wire, actual science Olympiad did for family science night. Aluminum wire, just looks like aluminum, put it into the solution of copper chloride. Well, the copper came out of solution, gave us this reddish looking precipitate. That's all copper there. And there's not very much wire that's left that's been in the solution. And there was bubbling right away when we put it in. It felt hot to the touch on the outside because it was exothermic. And now my solution is clear. That's because it's no longer copper chloride solution. It is aluminum chloride solution. So it's a clear solution now. Now that I have a little bit more of it in there, it's reacting a little bit more again. It only reacts so much as what we have reactants for. So if there's not enough to react with, it's going to stop its reaction. You're going to see that reaction in the lab tomorrow as well. You're going to be leaving them out overnight to get some final masses. Okay, general patterns and examples. It always follows this pattern of an element plus a compound forms a different element and a different compound. And this is what we were just talking through. So my aluminum wire went in to my copper chloride solution, and I got copper solid out and aluminum chloride. Is this reaction balanced? No. What is off on this one? Yeah, Cl3 and Cl2, absolutely. So my trick for this, if I ever see a 3 and a 2, I want to make them both equal 6 total. So I'm going to put a 3 as a coefficient in front of the CuCl2. So now I have 6 chlorines. My AlCl3, I'll put a 2 as my coefficient, so now I have 6 chlorines. Is it balanced now? No, my chlorines are, but the rest of it is not. So I need to put a 2 in front of my aluminum solid and a 3 in front of my copper solid. Questions on that? So notice when we add that solid, we produce a different solid. When we add a gas, we may get another gas, or we might actually get a solid from it. Okay, double replacement, also known as double displacement. Displacement. So this would be a good another flashcard for you. Double replacement synonym, and then on the back side, double displacement. This is our largest category of reactions. Quite often it's 2 solutions as the reactant. So I take 2 liquids that are dissolved, or 2 things that are dissolved in an aqueous solution of water, put them together. The products can take a lot of different forms, but it's usually one of the products is a solution. So one will still be aqueous. But we have those driving forces, so something's not just going to be aqueous, otherwise a reaction won't occur. So we might have a precipitate or a solid form. We might have a gas forming. We might have the formation of water, which would be those acid-base reactions, which is this part. So it includes acid-base reactions because of that driving force of forming water. Sorry. A lot of the time we'll get a precipitate, and we saw a picture of it up on the board yesterday, taking 2 clear colorless liquids, pouring them in together, and getting out a yellow precipitate, which I'm not sure if we'll do that lab this year or not. The leftover precipitate is very difficult to get rid of in an environmentally friendly way, so we might not do that one this year. Yeah. Okay. So our patterns for double replacement or double displacement, we're going to follow this pattern of a compound plus another compound, forms a new compound and a different new compound. In this example, you're going to see in the lab tomorrow as well. So sodium hydroxide solution plus copper 2 nitrate solution forms copper 2 hydroxide solid plus sodium nitrate solution. Later on in this year, we're going to talk about how we can predict whether or not we'll get a precipitate, whether we'll get that solid out or not. There's some very good rules to figuring that out. At this point, you just need to understand that precipitate means a solid. Is this one balanced? Give me a thumbs up if it's balanced, thumbs down if it's not balanced. Yeah, it's not balanced. So try to balance it on your sheet. Okay, I want you to use your hands to show me what the coefficients would be. If any of them you don't write something in front of, that means there's one of them, so I'll have you put up a 1 if that's the instance. So what will we put as a coefficient in front of sodium hydroxide? Yeah, 2. Good. 2 sodium hydroxides. Okay, show me what coefficient we would have in front of copper 2 nitrate. Yeah, I would have a 1, so I won't write anything out. 1 copper nitrate. Copper 2 nitrate, excuse me. Okay, other side. Copper 2 hydroxide, what will the coefficient be? Yeah, that one's just a 1 as well. And then the sodium nitrate, what will that be? Excellent. Lots of 2's. Good. Good. 2, 1, 1, 2 for this reaction. Questions on how we got there? Were we able to treat the polyatomics as groups, or did we have to split them up? Yeah, we got to treat them as groups. I had OH on both sides, and I had NO3 on both sides, so I could treat them as groups to make life much easier. Okay. So notice that we produced that precipitate, even though I had 2 aqueous